In progress.
Okay. Hello. So we are starting. So now when you are finished to create your model, you need to check under analysis, click on analysis. Then building analysis. We are supposed to be changing most of the parameters here, but then before you can think about changing most of those settings, we need to first go to analysis and check if your modeling is correct. So under analysis, you click on building model check. Then you click on start. So you confirm that you have 0 errors. Is that okay? You click on analysis, then building model check. It's going to run a check for your model and ensure that you have 0 errors. Okay? Now, close that. Let's click on the settings center on the quick access toolbar up here. The settings center. So in the settings center, you're going to provide the design preferences which you're going to use. So the codes are okay. We are using Eurocode. That's the first item we took. Then what are we going to be designing? We are going to be designing columns. So under here, there's column and shear wall. Expand column and shear wall. You check under rebars. There's that arrow which is next to all these items. Once you click on it, it will expand or diminish the contents inside. So expand column and shear wall, then expand rebars. Are we there? Okay. So let's click on the settings center up here. Remember where we adjusted the dimensions. That's the icon we are looking for. The settings center. Then check. You'll see column and shear wall here. You can see it. Click on the arrow next to it. Then you'll see 3 items there. There is design, rebars, and detailing. Expand rebars, click on the arrow which is next to rebars. So from here, we are interested in setting the sizes of bars to use in columns. Okay, so you look at the selection method. We have fixed bar layout method, bar spacing maximization method, and bar minimization bus size minimization method. Okay, so you are going to keep all these default unless you're working on area reinforcement, which is like maybe a slab where you need to annotate reinforcements with spacing, then you can adopt maybe either of the two. Okay, so let's look at longitudinal bars. Under longitudinal bars, have you done design of reinforced concrete structures in class? Okay, so now here, when you're selecting these sizes, Eurocode has it that when you're designing a column, the minimum number of bars you can have in a column is 4, if it is a square or rectangular section. If it is a square or rectangular section, the minimum number of bars you can have in a column is 4. Okay? And the minimum size of the bars you can have in a column is 12. Okay? That's the diameter of bars. The minimum you can have in a column is 12. So these bars they are given a prefix. You can call them T, you can call them H. Okay, so that prefix, it can mean it means either high tensile or low tensile steel. Okay, so but Eurocode uses a T. Okay, so but right now here we are having H12 and H32. So based on the code, this is already predetermined. Okay, but then you are prompted to choose the maximum bar size. When you are designing a structure, we are looking at the cost effectiveness of the project. So when we are making judgment, it's either area of concrete or number of reinforcements that you're going to have in a section. So on market, steel is more expensive compared to concrete. So even here, the higher the size, even the cost will be increasing. Now, let's have this limited to 20. The maximum is going to be 20. But even still, when you find that your client is loaded, you can design up to 32. But what is going to limit you here, the client can have that money to buy that T32. But then if you check on the manufacturer, where are you going to get that steel? Do they have that high like the bar size? If they don't have it, then you can put it to the one which is next to the one which they have, like the one which is next to 32. You get it? So let's limit this to 20, but we are not saying that this column is going to have 12 and 20. So this is a range. As you are designing, the software is going to iterate between 12 and 20. If it finds that maybe 16 is passing, then it will give you a choice of 16. You get it? If it finds that I need something above my maximum, it will give it a failure. That's when you run your reports and find that the software is giving you a report of an element which is failing because your maximum is not passing the checks. So we are going to reach that stage. So here we have column bar size, and then you also have wall bar size. When you're designing in portal structure, columns are taken, walls are taken to be columns, but over longer span. Okay, they all resist load or they bear the axial loading through compression. They are all compression members. Okay, so when you're designing, you design them all at once. Okay, so in our project, we don't have walls, but after we've run through the analysis and design, I'll make an illustration of how you can create walls using Proto structure, like how you can design lift shaft walls. Get it? So here, even if we now choose any preferences, it will not make any impact because you don't have this design element in your model. So let's have it as 10 and a maximum of 12. Now, those wall loads which we put on the beams, they are calculated internally. And then they are transferred onto the beams. The beams take them to the columns. But the walls I meant walls like reinforced concrete walls. They are not masonry walls. So the walls which are designed here, they are reinforced concrete walls, like lift shaft walls, basement walls, retaining walls, those kinds of walls. Yeah. So at this point, you need also choose the concrete cover. If you don't choose the concrete cover, this program is going to use a value of 25, which is right from the code. So here you are free to put a figure or leave it blank. So if you leave it blank, it will use a value of 25. The column size. Okay, let me cast something here to explain this very well. Okay, so I shared this file with you, you have it. Now this is a column. This is our label for the columns. Only that here we have two columns. This is a special case. This was a special case for this project. But then the white membranes you are seeing there, those are expansion membranes. Usually when we are building, when you are designing a building which is too long, there's need to provide expansion joints, such that in the event of maybe any lateral loading, or maybe the building has developed cracks, those cracks are not transferred to the rest of the structure. So we put those expansion joints to terminate extent of failure, and also during conditions of maybe high and low temperatures. So these membranes, they help a lot. Now, the question she was asking about longitudinal bars, why we are choosing 12 and then a maximum of 20. See, in a column, we have typically two types of bars. You have the longitudinal reinforcements. These are the bars which are vertical. Okay? And then you also have, they are called ties. Okay? So in a column, we call these ones ties. But then in beams, we call them links. Okay? So on site, you find that they will be using a term called stirrups. They will mean the same thing. Okay? But they are called ties. Now we have ties and longitudinal reinforcements. The preferences that we are choosing here, a minimum of 12 and a maximum of 20, we are referring to these ones which are vertical only. You get it? So you find that in this column, you can have bars of T16. And then in this other column, you can have bars of T20. Okay. But then in your overall project, when you're designing, the software is not going to opt for a bar which is beyond 20, and it's not going to opt for a bar which is less than 12. You get what I mean? Yes. Now, when we are talking about concrete cover here, for concrete cover, now I need you to look at all of us have done the first industrial training, right? You have done recess. So have you got a chance to look at when they are erecting columns on site? Okay. Now, now assuming this is my column, after it has been cast fully, even with the bars inside. This is the first bar, the next bar, this bar, and this bar. A cross section on plan. So for you to achieve this size or this cross section here, there must be some form of formwork. Okay. So that formwork is called a kicker, which you place at the base or at the starting point of the slab to come up with this shape. Okay. So that formwork is called a kicker, which is displayed as this. I don't know if I can isolate this one out. View image. Okay, so now this is the formwork I'm talking about. So before casting these columns, you need to provide like a space between the reinforcements and okay, to come up with the actual cross section of that column. So we need a space where you find that the aggregates are going to pass. So this space which is left between this formwork up to where the reinforcement is, that's the concrete cover. Okay. So the concrete cover for Eurocode, it recommends a value of 25. But in most cases, when you are on site, you find that they give a value of beyond 30, okay, between 30 to 50. Okay. So when you design for a value of 30, therefore also on site, this concrete cover must be adopted as 30. So that is the value which is supposed to reflect in the general notes of your structural drawings. You get it? Okay. So now the concrete cover which we are going to give is going to be 30. Okay. So let's have a value of 30 here. Then we have maximum column steel bar spacing and minimum steel bar spacing, a value of 25 and a value of 200 maximum. Assuming that this is your cross section, we are having a cross section of 200 by 200. Okay, so this is 200. This side also, this side is 200. Now, the distance between this bar and this bar, centroid, like center of the bar to center of the bar. Then you also have concrete cover. So this, if we get 200 overall, we deduct concrete cover either side. That leaves us with 2 times, you have a concrete cover of 30. Okay, so I've got this overall 200 minus this side, okay, this space and this space. Then we have up to the center of the bars, assuming that we are using bars of 16. Okay, so you're going to deduct how much? It's 8 times 2. So that will be 16 divided by 2 twice. So okay, this leaves you with how much? 124. Okay, assuming now I'm placing another bar around here. Okay, so the spacing that is left is going to be minus maybe let me repeat this. Okay, I now need the space between, okay, to face of reinforcement, face of reinforcement. So it's going to be 200 minus 2 times 30 minus 2 times 16. Thank you. So that leaves you with 108. Then if I have another bar added here, still of 16. So it leaves you with minus 16, it leaves you with 92. Okay. So this value here, on a worst case for a section of 200 by 200, you can have only 3 bars. If you place another bar of 16, they become 4. So that leaves you with how much? Minus 16 here. Is it 78? Okay. So we don't push it to a very small space, because in between here, you also need to have the aggregates. Okay. So assuming that now you have an aggregate which is of a bigger size, it will not be able to pass through smoothly. Okay. So we keep those preferences the way they are. Okay. Reason being, if you alternate those preferences, you're going to end up with spaces which are very small and your maximum aggregate size might interfere with the design constraints. You get it? So that's when you find issues of segregation on site, if bars are closely packed. Okay? Now, if you are to change this minimum spacing, the least minimum value that you can have here is going to be the maximum aggregate size, add 5. Okay? So that maximum aggregate size, you need to follow it up because it is determined at a stage where you also where you are monitoring the workability of the concrete that will be used. So when you're making the slump test, you'll be required to specify the maximum aggregate size that will be used. Okay. So on site, when they're doing that slump test, the aggregate size that they will be using, it will be from this design stage. Okay. So you keep that value the way it is, and also those values the way they are, don't change. Now we go to links. So here it calls it links, but in actual sense we are looking at ties. Now for the links, we are going to use H8. So you can take this to be the same as the shear reinforcement. So when you're talking about shear reinforcement, those are the links. They majorly help in controlling cracks in a structural element, be it a beam, be it a column. Okay. So these links, we take the minimum size. Then the minimum link spacing, you can have 100, then the maximum can be 300. Okay. So if you limit it here to a spacing of, let's say, 200, you find that even with a spacing of 300, will be passing. Okay. So let's keep it to the maximum spacing. And then we have the spacing step. So if the software calculates and finds that maybe a spacing of 175 is not passing, it will shift in increments of 25 and it goes to 200, 225, 250, like that. So that's the spacing step. Likewise for the horizontal bar spacing, sorry, the wall horizontal bar maximum spacing. Let's keep all these ones default. Now we have this condition, create support regions for links. So on site, when they are tying those bars, assuming this is my column, I'm at top of slab here, then here also this is the soffit of the upper slab. So those links, they are going to be provided at a given spacing. Okay. So we take this to be a support region, and also this one to be a support region. Okay. They are called confinement zones. We have 3 confinement zones, be it in a column or be it in a beam. Okay. So near support, this is the first confinement zone. We have those links closely spaced. As you go towards the center of the structural element, the spacing increases. Then as you turn towards the support region, you have them closely spaced. But then on site, it is on a rare case that you find something like this. For them, they'll have uniform spacing. So also when you are design for uniform spacing, unless you're going to be there and like enforce this kind of reinforcement, curtailment. Okay, so that option, leave it unmarked. Then here we have provision of links through the beam depth. When you look at this is the beam, I'm having this as the column and then this as the beam. Okay. Now, when I'm having, you see these stirrups here. There are some stirrups which are passing through the beam. Okay. But then this would mean that casting of this column and this beam, they are going to do, it's going to happen at once. Okay. But then in a scenario where I find that you're going to first cast the column, you're not going to have these links through the depth of the beam. Okay. So if in case you want these links to go through the depth of the beam, well, that is a feature that you can also add in your design, providing link through beam depth. You can keep it marked. Then under detailing, we go to general. We have the rebar bob control. For reinforcements which will be at the topmost level of the structure, how will they be cranked? So you can either choose this option or this option, whichever you choose is okay. Okay, so you go with the other option, this other option, but then we have these other factors which you can also change. So in portal structure, what is called a bob, that is a hook. You find this terminology, bob, as well in foundations and also in beams. So when they're talking about bobs, that is a hook. Like for example here, if I can refer to this foundation, you say this return here of about 150 mm. This is the bob. So the length of this bob right now, in terms of columns, they are referring to if you have a bar which comes and it's the last bar, how will it be ended? It will be ended with a hook like that. So what's the length of this hook? What is going to determine the length of that hook is going to be that factor which you're seeing there, which is 5 times the diameter of that bar. So that will happen internally in the software. So once you've got the preferred sizes of the longitudinal bars, that length will be automatically catered for. So it is from here that now you can even judge based on the size of your structure. You can tell that this structure is maybe it is too big, it's having heavy loading. I'm going to use maybe T20 bars. So if it is T20, you can determine the size of that hook, how it will be. It will be 5 times 20. So basically, what we set here is this, and also the position for laps. For columns, do you want to lap at mid height or you want to lap at top of slab? Usually on site, after casting the upper slab, they will leave startup bars where you have continuity of the column. So at that stage, lapping is done at top of slab. This is the first option. But you also have an option of lapping at mid height. So let's take it with the first option. And also in scenarios where you have single links or single ties, this is taken to be more stronger. Okay. This is a single link. Assuming this is microsection, and I'm having a bar here and another bar here, another bar here, another bar here. So if they are to be given a single link, it will be like this. Not like this. So this one is less stronger compared to this, isn't it? Then let's look at the beam. Let's go to beam, expand beam, and look at parameters. Under parameters, you have floor beams. You also have rib beams and foundation beams. Maybe to start with foundation beams, those are the beams which you drew in story 0 at the beginning. So those beams which you try to take onto upper levels and they refused, those are foundation beams. They are created at the level where you have the foundation. So we don't have foundation beams in our project. So let's look at now rib beams. For rib beams, the minimum diameter of steel, you can take from 10 to 16. Maximum is going to be 16. Why I'm choosing 16? The minimum diameter of bars in a beam is 10. Okay? And the maximum diameter of bars in a beam is not defined. Okay? I'm using the minimum as 10 because when you have your ribbed slab, you have another layer of BRC on top. So that BRC is also extra reinforcement. But then what we are talking about here, these are bars which are going to be added in the ribs only. Okay, so in case 10 is not passing, it can opt for 16. But then having 20, it will be too much. Yeah? For floor beams, we have not yet reached there. After rib beams, we are getting to floor beams. Then we also have minimum number of hanger bars. Hanger bars, those are the bars in the tension zone of a beam. Sorry, in the compression zone of a beam. So if this is your beam, assuming this is the elevation detail, I'll have a bar at this point running from that side up to here. I'll also have another bar at the bottom. Okay. Now, hanger bars, those are bars in this region. At the top, these are the hanger bars. So, and the top is taken to be the tension zone. This is the tension zone of a beam. When it is subjected to a load, if I have like axial loading at this point, let's say P. So the behavior of this beam is going to be in this format. Okay. Actually, yeah, this is the compression zone. Okay, this is the compression zone, and then this is the tension zone down. So the hanger bars are in the compression zone. Okay, so here, um, and then at this point here, it will be like this. So the hanger bars are in this region here. Okay. So the minimum is going to be 2. But usually there's some projects like the residentials. I see some people putting 3 bars. The minimum number of bars in a beam according to standards is 4. If it is a square or rectangular section, it should be 4. If there are 4, then the minimum number of hanger bars is going to be 2. If you limit it, okay, if you put 3 here, then also when you're designing, it's going to give you 3 bars at the top. But when you're putting 3 bars, you might find that even 2 bars can pass when you're designing. So meaning you have already over-designed before you finished, before you have started designing. You get it? So let's limit it to 2. Unless it is failing, then Plotter will give us an option of having a 3rd bar. Then the minimum number of hanger bar diameter is going to be 12. Okay, here we are looking at rib beams. It's going to be 10. And then the links can keep 8. And also maximum is going to be 8. Then concrete cover, if you don't put any value, it will use a value of 20. You have beam top, beam bottom, section side, and also beam ends. So let's keep all this default. Then we go to this point here, steel bar properties, steel bar cut length. What's the standard length of a bar? The standard length of steel is 12 meters. It's 12 meters. But then on site, you need to put in some allowance. They might bring bars which are not exactly 12 meters. Okay. So it is at this stage that then you can maybe put this to be at 11,500. Okay. Just in case the materials which they have brought are not to standard, you are still safe. So once you put this value here as 11,500, you need to make sure that you use that same value for all your other structural design elements. Okay, columns, beams, foundations, take that length. Because once you divert, you're going to mix up values of the bar bending schedule. So let's keep all this default, and then we come to the link properties. The maximum spacing can take it to be 300, and also here 100. Let's keep also this default. Then I'll go to steel bar selection, expand steel bar selection. The selection method you keep it in spacing optimization method. Okay. And then in the design, the reinforcement pattern. This is very important. The reinforcement pattern, whatever pattern you choose here, that is exactly how your details will come up. For some people who want to use automatic generated details, if I choose standard pattern number 1, you can see how bars will be lapped. Standard pattern number 3 will be like that. Okay, so you choose one which is convenient for you. But 3D is taken to be the best pattern compared to these others. Okay. But then in proto structure 2025, from 2025, 2026, there are some more patterns which they included just to add different ways of how you can curtail rebar in a beam. So here you opt for pattern number 3. Then at this point, do you want to use same bus size in first and second layer? You shouldn't mark this option. And also this option should be left unmarked. So if we have designed, yes, that's what I'm explaining. If we have designed and Proto finds out that I have this bar, this bar, this bar, and this bar. So these are 4 bars in a beam. But then if the program finds out that these bars are not enough, and maybe you need 5 bars, usually those additional bars, they are either at the bottom of the beam, because that is where you expect tension. Okay. So it's either at the bottom of the beam or at the top of the beam. If they are at the top of the beam, that means that at the support, where you have the beam crossing the column, that's where I put additional reinforcements. Because if I'm assuming this is your base frame, columns and beams, when this beam is deflecting, it's going to deflect in this format. Okay, so at the support, we have hogging moments. At this point here, we have hogging moments. These are called hogging moments. So usually when you look at a scenario where you find that you need more bars at the top, that means that it will be along this beam, it will be near support. That is a section which is cut at this point. If I cut a section through this beam and I look this side, so to reduce these hogging moments, you find that you need to add an extra bar here. If I cut a section at that point, this can be the section here. And also this section can also apply at this point. But then you can find a scenario where you find that the additional bar is at the bottom. So that means that that section has been cut through at this area. Okay. And it's not a must that the section which you're going to get at this point and at this point, they are going to be the same. They can be different based on the load, like, okay, the beam from this end and the beam from this end, they can be receiving different loading. So the loading at this point and at this point can be different. Therefore, also this section can change. You get it? So it is very important in your details, beam elevation details, to show those changes where you have additional reinforcements, basically at the support and also mid-span. So now, if the program finds out that you need 5 bars, you can just add it here. You have the first layer. This is the first layer at the top, first layer at the bottom. But then if you find that you need more bars, let's say 6 bars, okay? So you're going to have another bar added here. But then this will create an imbalance in a section. You can't have this bar at this point here, and then you fail to add another bar here, okay? So this is another layer. The first layer at the top, the second layer at the top. When you look at this cross section, if I put a dashed line here and another dashed line at the center, this is called the neutral axis. So on the upper side of the neutral axis and the lower side of the neutral axis, you can have different layers. So 2 layers at the top, 1 layer at the bottom. But there are scenarios where I find that you need a bar at this point, and also this point. Bars which are placed at the neutral axis, they help in controlling cracks. Those are called side face reinforcements. And also if you misinterpret this cross section, and instead of having these bars placed at this point and you place them at this point, you have made a very big error, because at this point we do not have moments. Okay, we don't have moments here at the neutral axis. So whatever you are suggesting to have layers of reinforcements, place them above or below the neutral axis, unless they are deep beams. It's usually for deep beams that we provide side face reinforcements. Beams which have a depth from 600 onwards, that's when you provide side face reinforcement. So you can leave this option out. I've not marked this simply because use same bars size in first and second layer. That can change on site. You may find that here I can have a bigger diameter, and these ones, this can be 20 and this can be 16. Okay, so that rules out this option. And then this other option, use same number of bars in first and second layer. It contradicts with what we have actually even here. Here I'm having 3, here I'm having 2. Okay, if you mark that option, you'll be limited to 2, 2. You get it? Then the rest, let's leave them default. Now we have bent up bars. You need to come here, basically for slabs and beams, confirm that you're not using bent up bars. Okay, so bent up bars, this is another form of curtailment, of reinforcement, but usually it is not used in our industry. Okay, so for us we use straight bars. So this option, you leave it as no bent up bars. Okay, you just need to confirm, don't change. So for floor beams, no bent up bars. Also for rib beams, confirm that you don't have bent up bars. Okay. Then links. When you come to links, confirm this point that it is standard. Rebar, so rib links type is make it closed. And the rib links should be closed. There is this extension of 500. That extension of 500 caters for the extra length which is added onto the links. But just keep it the way it is. Yeah? Yeah, it should be standard. Make it standard. Initially, it will be closed, but make it to be standard. Okay, for curtailment, look into curtailment, steel bars. Under curtailment, we have the first option of steel bars. You're going to keep this default lap outside the support. Then we have these other options, merge similar bottom span bars. Okay, if we design and find out that a bar which comes like this, it meets a support, is going to be terminated at that support. But then if it is T16 and you find that it is having like maybe 3 meter length, but you still have extra length that it can run, if it is 16, it has to be 1 bar, okay? If they are different, 16 and 20, they are going to be split. So this first option here helps us in making sure that if the bar is of the same type and it's continuous, it should be merged, it should be 1 bar. This option, you mark it. Also this option, you mark it. The rest, let's leave them default. You got steel bars too. Okay. You don't change anything, keep it the way it is. Then you go to bob control. In the bob control, we have cantilevers in our project. Mark to draw bobs for cantilever bottom bars. Initially, it will be like that, but then we need to see that at the bottom, the bar has a return, which is going to be fixing into the top hook, okay? So for the cantilever, then how is the setup of that return bar of those bobs? We have this option, we have this option, okay? So any which you choose is okay. Keep it in the first option or in the last option, any of these two. Under detailing, detailed drawings. Yes, please. If we have these extensions, it's not wastage. This is you're catering for anchoring of those bars into the next structural element. It's not wastage. By the fact that you have designed for it, even the reinforcements that you're going to get will also be catering for that same. It's not wastage. Yeah. Then under detailed drawings, general, confirm that this is 11,500. Remember when we say that the steel bar length, 11.5 meters, also change it to 11.5 meters to be consistent. This is for walls. Then replotting bars below the beam, it's not necessary. Keep all those ones the way they are. Then we go to beams. Under beams, confirm that you have marked this option, shift outer layer bars to enhance display. Okay. Then if you want, you can underline the beam labels. You can print them below the detail. Okay, if you want, you can display beam reference levels. This will show you that maybe on first floor, second floor, like that, but that is not necessary. Okay. Then let's look at sections. Under sections, you have beam sections or no sections. If you leave it in no sections, you'll not be able to get the supports and span cross sections next to your beam elevation detail. And they are very, very important. Okay. So you can decide to do for different beams. Or for all beams. What do they mean with different beams and then for all beams? Okay. So different beams, these are unique sections. I can start with a section which is having a depth of 400 here. Then this has a depth of 600. So if that is the case, if it is in different beams, it will give you a section here and also a section for the next span. But then you would consider having for all the beams. Okay. Then number of sections, you can do span section only or support span. Which of the two can we go with? Yeah, support and span. Then how they will be annotated, you can choose either alphabets, uppercase or lowercase or numbers. I'll leave it in uppercase. Then steel bars and links. You see, under general, under beams, we mark to shift outside layer of bars enhanced display. We are still getting it in this next option, steel bars and links. Under steel bars and links, when you look at that preview, you need it's like if you have a second layer, you may not see it very well. But if in case you shift the outside layer of bars enhance display, you'll see those two layers of bars at the top. Okay, if you look at that element. Then let's also apply cranks to steel bars and also display bulbs as shifted. Then also the link detail, we can print it in line or above line, where there's this option, draw link labels in line, but it's best to unmark it and also print it inside the beam. If I unmark here, it will be printed outside the beam. Okay. Then the other thing is, okay, we don't have sidebars. Under dimensioning, remove dimension bulbs. Okay. Confirm that you don't have dimension bulbs. And then also dimensioning of span supports columns and clear spans. Remove it because it's more like a repetition of the detail which is above. Okay. So whatever we are removing, we are trying to make the drawing not so busy. So unmarked dimension support columns and clear spans. Unmarked dimension bulbs. Yeah, that's it. Then we need to, okay, detailing, let's keep it default. This deals with water detail sheets. So let's go to slab. Under slab, for design of slab, confirm that it is, how is this? Under rebars. Okay, in design, we are going to use centerline span. Okay, so this is the effective span. Then in rebars, confirm that you have straight bars, not bent up bars. Okay, so it should be straight bars. You have the minimum steel bar size. It's 10. Bar spacing, minimum and maximum, let's keep it to 50. And leave all these others default. Length step, spacing step. Also, you need to confirm the cutting length of the bars. Okay. So 11,500, that back cutting length, you can keep it 12 meters, but since I had changed it already, I just need to be consistent. Then in the appearance, this is very important. In the appearance, confirm that you are showing the number of bars in the detail, and also you're printing alternative layer information. Alternative layer information, they mean if this is my slab, I have this bar from this end up to that end. I have this bar, this end, that end. When I'm detailing, I'll detail this, like I'll annotate for this bar to span from this point to that point, I'll represent it with a dot. Okay. So if these are like 18 T20s with a bar mark of, let's say, 0.3 and a spacing of, let's say, 150. Center to center. So I don't know, is this top reinforcement or bottom reinforcement? This can be bottom reinforcement, and it can be bottom reinforcement in direction 1. So then this one here, I'll annotate it in this format. I will show that this bar runs from this point up to that point. I'll put a point of emphasis that I'm talking about that bar. They might be like maybe 15 T20s. So it's going to be bar mark 0.4 at a spacing of, let's say, 175. Center to center. So I need to know, is this bottom reinforcement or top reinforcement? Is this bottom reinforcement or top reinforcement? It is still bottom reinforcement. Okay, it's still bottom reinforcement. I have at the bottom bars running like this, and also a mat of bars running like this. So yes, it's just a label to show the like tensile strength. We shall later on change it to T because that is what Eurocode has. But then as you are starting to just configure, it will be in any alphabet. Okay. So after you've changed the grade of steel, that's when it will have to change. We are looking at it later. Okay, but it means tensile strength. Bar mark, I'm coming. That's what I'm trying to explain right now. Now, this is a slab. You see, on this slab, there is a mat at the bottom, okay? Bars running this direction and that direction, okay? This bar here, and then this other bar. But then you also have a top mat running in the same configuration, still both directions, bottom and top. Now, what I mean with bar mark, now bar mark, that is an ID which is given to reinforcement, which is changing in a particular confinement zone. Okay, so when you look at this bar here, is going to be having a different length compared to this bar, isn't it? So whenever you have a change in length of bars, whenever you have a change of length, a change of bar type, if this is T16 and this is T20, those are different bar marks. If this is T16 and this is T16, they have the same length, but the direction is different. That is a different bar mark. Bar mark, just take it just as a random number which uniquely identifies a different type of bar. You get it? So, but what affects it is the change in length of the bars, change in type of the bars, and also the direction of bars. Now, protostructure is not going to give you a detail which looks like this, but this is how you represent your details after design or after detailing. Okay, so this is number of bars, bar type, bar mark, spacing, and then like an ID, bottom or top reinforcement. So Prota has it that in Prota you find that this is bottom representing B1. Okay, so you find B2, it will be bottom top. Okay, but they are all bottom reinforcement. Now, when it comes to the top mat, Prota will represent it as top, bottom, and then top, starts with top, that is T1. Okay. And then top, bottom, that is T2. So when you find this kind of scenario, this is how it will look like. What do they mean with top, and then top, bottom? We have seen that if it starts with the T, it's top reinforcement. Okay. So when you are looking at top reinforcement, one bar will be on top of the other. One will be below. So one which is on top, this is top. This is top, bottom. Then we'll go to bottom reinforcement. This is the bottom, top. And then the one which is right at the soffit is bottom. You get it? Eh? Okay. Yes, after that, now we need to come to foundation under general. So what we are setting here is the steel. So under steel bar selection, footing reinforcements with bobs. Do you need it with bobs? Does it need to have bobs? Do you know what bobs are? Yes? Anyone who knows what a bob is? Yes? It's a what? That is a hook. Okay? Yes, it is a hook. Okay, so does this this is the footing, eh? Does this footing have bobs? You definitely need bobs, eh? That is a must. There's no scenario where I don't need bobs. Yeah, the option is there. You say the options, but then when you look at the strength, because now those bars they need to tie each other, hold each other rigidity. So we need to have bobs. Then the minimum steel bar size let's have a steel bar based on the kind of structure that we have modeled. Let's have steel bar sizes of minimum 16 and also 16 here. Okay, just keep that default. Do you want to use top bars? Do we use top bars in foundations? Yes, it depends on how, on what. Now, this footing doesn't have top bars. They're not, there's no top mat. But scenarios where if you have combined footings, we need to use top reinforcement. Okay. So where you have combined footings, we use top reinforcements. But then at this stage, at the stage at which we are not sure if we are going to have combined footings or not. So if we use top bars, it might give us an over design. Okay. So when you're starting, let's not use top bars. Then when we find out that we have combined footings, we might have to come back and tick that option. But also we can configure it right from the interactive design stage. Then what is key here for foundations is steel bar selection and then the footing size, the minimum pad base depth. We had an initial pad footing depth of what? Of 400. So if you put 400 here, you'll be limited to 400. Even still, even if a pad depth of 300 would be okay, the program will not give you that pad. Okay? So based on practice, let's have this to be 300. Okay? Minimum and the width you keep it as 1 meter. Then we have lean concrete thickness. Do we know lean concrete? Yes. That is concrete without reinforcement. You are very true. That is concrete without reinforcement. But lean concrete, it doesn't have reinforcements, but still, why it is called lean concrete, it's concrete of a weak mix. Do we know blinding? Concrete blinding. So concrete blinding, when you look at this footing, there's concrete which has been cast there. So that is the layer of concrete that is placed before you put the reinforcements. The reason for blinding is to avoid reinforcements having direct contact with the soil, because soil already has moisture, and when the reinforcements are in contact with that moisture, there will be early development of corrosion in the reinforcements. Okay, now we have the soil unit weight. Do you know what unit weight is? That is the density of the material. Okay, you remember when we are trying to configure the wall loads, we are trying to choose different materials, blocks, bricks, choosing from the different unit weights which were allocated. Okay, so unit weight is density of the material. So here we specify the unit weight of the soil. So this, you get it from the geotechnical investigation report. All these properties are given there. Properties of the soil, then the allowable bearing capacity of the soil. We need to enter it here. Why you do geotech is purposely to have this value and also be sure of this value. Those are the two core, actually there are three. We have this unit weight, bearing capacity, and also the subgrade modulus. The subgrade coefficient of the soil. This is shown in the soil profile, which is given in the geotechnical investigation report. So if you are not sure of that value, you go with the default value of 5,000 or is it 50,000? Okay. So also if you're not sure of the allowable bearing capacity, go with the default value of 200. But then you can also click on select and choose the subgrade modulus from within these ranges. But it will be defined in the report by the experts. Yes. Yes, please. Yes, that is true. That load that is coming from up is sitting on that on the footing is called the on the concrete which is responsible for the footing. So this concrete blinding, it doesn't play any role in regards to the strength behavior of the structure. No. Remember, your foundation, which you are designing for the other footing, the other base depth. You get it? So it is the other base depth that is bearing all that load, not this lean concrete. Yeah. Okay, so that is it for foundations. And usually the thickness of that lean concrete is 100. Then confirm under rebar, go to rebar, then rebar label. Scroll down, you'll see where there is scales, rebar, expand rebar. Then you click at rebar label. In the rebar label, confirm that you have shown that layer information. This is going to help us for the option which we activated in the slab, alternative layer information. Okay, so confirm, you mark that. Then also the layer separator, it will be like that. So here I'm putting a bracket, it will be represented like, it will add a bracket here like this. The separator character. Then the rest, let's leave them default. Now, allow me take you back slightly to label, okay? expand label, under settings. Okay, under settings. If you have been noticing our detail, if this is our beam, the one we have been modeling, and this is the column. Also, this is the column. You've been having, maybe if it is a C2 something here, column number, but then also the beam label has been is added around here next to the support. It has been 200 by 400 with a slash by 400 like that, but next to the column. That is in the detail, so in the model. Now, it is better we represent our detail like this. This is your support. The column mark can stay there, but then that beam detail should be at least in the center of the beam. You get it? So we are going to represent our detail, like let's say if it is 200 by 400. Like that. Okay, so this makes it look a bit better and professional. Okay. Now, what we are changing in that label settings for the beam is the separator and also the positioning of that detail. So under settings, you click on label and dimension position. When I click there, it will keep shifting to the position where I need that label to be. Okay. So you just need to click until you find that your label has been positioned in the center of the beam. Is that okay? You click there, it will shift to different positions. Just click until you find that it is positioned the way you want it to be. Then the separator, we can get it from template. Under templates, you click on where the size separator, put X. Okay, where there is the size separator, put X. Put X. And then okay, so let's click OK. Are we all on the same page? Yes, what is? I'm speedy. You're waiting me to click OK. Yeah. So I'll click OK. So this is the problem. So update concrete cover, you click yes. Now, what we have just gone through, you see, when you're starting the project, Structure scheming, positioning of structural members. That is the core step of design, followed by what we have just done. Okay. Now, based on the preferences that we have set, I need you to click on views. First of all, save this project. This whole loading had to be changed to 1.5. If you changed it, that's okay. You did 1.4. You did, it's okay. So if you changed, it's okay. Me, I didn't change, so there's no time for changing that. Yeah, you can go back. Yes, the other settings that we have configured, if you find that maybe you need to make some alteration, you can switch back and change. But the project is going to be designed and analyzed based on those settings. Okay. So I need you to click on views. You click on tile vertical. Tile vertical. So when you click tile vertical, you now have two viewports. If you need to go back to the other one viewport, you can click on reset. Reset, and then to shift back. So I needed two viewports such that whatever I'm doing in the floor plan, I can visualize directly in the 3D. Okay, now make sure that the plan viewport has been activated. It should be highlighting blue. Click there and confirm that it's the one which has been activated. Then we go to analysis, building analysis. Okay. So we are in building analysis. So we start with the pre-analysis checks. Click on project parameters. Under foundations, confirm your allowable bearing soil stress. Okay, confirm it is 200. If you had changed it in the other side, you need to confirm here and change it. Then lateral loading, you keep it default. Lateral drift, under lateral drift, this will work for either you want to change the bracing system of the structure. So the columns, we are designing braced or unbraced columns. Yes. Yes. If the load exceeds 200, you will need a foundation which supports that load. If it exceeds 200, it will definitely exceed for some of the parts. But then that is why you are designing. You are designing for that particular load which is exceeding a soil stress of 200. You get it? So if it exceeds, that means it is definitely failing there. But if it is failing, you need to make a design which suits that magnitude of load. You get it? So in the end, actually, this is your pad. This is your column. Your design has that the allowable soil stress is 200. Now, you get bearing pressures at these corners. Bearing pressure at this point, and this point, and at this point. At no occasion that you'll find that the pressure which is at this point, or this point, or this point is more than 200. You get it? So in your foundation design, it should reflect that. But the moment you reach that stage, when it is not showing that, when it is showing that they are less than 200, then that means that the foundation is okay. You get it? Yeah. So I was saying, at this point where we are deciding to choose either we are designing columns when they are braced or unbraced. So that's going to be dictated by the methodology of construction. If they are going to first erect the frames before putting infill walls, then that is a braced system. Okay. So if it's just a frame, you design your columns when they are unbraced. But then if they are going to do walling at the same time, casting of the columns and also the beams when they are moving all at once. So your supporting system is going to be braced. Okay. So both walls and columns, just keep them braced and then come to title. You can put your project header. Maybe if this is the training project, training residential project, something like that. Training residential project. It is made by, you put your initials, you can put your name here. Checked by the engineer who is going to check your work. Then the project number you specify. Say these projects are going to have unique numbers, unique job descriptions, how they are identified according to your company. So it's not standard. The project date, you put all that information. Why you put it there at this stage is when you are trying to generate your reports, that information will be reflected in the reports manager. So if it's not added there, then also the reports manager will not reflect that information. But it's not a must that it should be there. You get it? Yeah. So I'll click OK. So that is in the project parameters. Let's click on loading combinations. Let's click on loading combinations. Now, you must have tested. Has anyone tried to create design strips? Has anyone tried to create or draw slab strips? Okay. Now, we are going to design the slabs through the design strips. Design strips help us in calculating the exact area of reinforcements which are required in a slab. But then for you to create those strips, you'll need load combinations first. So I was hoping that maybe one of you tried to draw something or do something which I've not talked about in class. You have not tested. Okay. So we need to first create load combinations. So we click on loading generator. Then in the loading generator, you tick all these three boxes, this, and that. Then you click on horizontal load combinations. You mark to include wind loading. Yes, you mark to include wind loading. Vertical load combinations don't include. Vertical load combinations will work for the where we have seismic analysis. So in our project, excluding seismic design, because that is advanced analysis. So let's look at, you've marked wind loading. You click OK. So later on, when in class you learn about nonlinear analysis. So the analysis that we are doing right now is static analysis. Static analysis does not include seismic action and does not include P delta analysis. So when you are into nonlinear analysis, that's when you include P delta effects or second order effects on your project. And it's also, there's another component called response spectrum analysis, which you also incorporate in that kind of analysis. But then for our project, let's focus on static analysis. Okay, so let's click on OK. When you're generating load combinations, you have commanded to include wind loading. But have you calculated that wind loading which you're including there? You have not calculated it. So follow it up with the wind load and story survey. Wind and story survey, you click on wind load calculator. This basic wind speed is known. That's a known value. So depending on where the site is, I don't know, you can check with the meteorological center, all these guys who do ATC, who do telecom masts or towers, they have that information, okay? So let's have a value of 30. And wind is going to apply in primarily two directions. So that is at 0 degrees and at 90, okay? So we need to provide a minimum wind pressure. Let's put a value of 0.65. And the primary wind angle is going to be at 0 degrees first. Then we look at all these elements here. What has been defined here has been elaborated in this image here. So where your site is situated, what is the height of that hill? Is it next to a hill? What is its height? Okay. So you provide that height here. Also x, that is the horizontal distance of the site from the top of the crest, has been indicated here, x. Okay. So, but usually we take these values default, LU, LD. Then you look at the terrain category based on the description of your site. Is it an area with low vegetation such as grass or isolated obstacles? You take whichever suits your site. I'll click OK. Then you specify the building category. Is it a reinforced concrete structure? Is it a steel structure, composite, or RC tower? Which one? What kind of structure are we dealing with? Reinforced concrete. Then we need to click on create report in case we need this report to reflect in the reports manager. You click on create report. Give it some time to process the wind load report. So this report, you can click here to Office or PDF. You can put it in PDF or take it to Office. Or you can save it to Microsoft Word 2007 or okay. So let's just close that window. Come to that. Yeah. So you it's the reports manager. Then let's close that window. You click on apply and then OK. You have calculated your load. How many types of loads have we included in our project? How many types of loads have we included in our project? Anyone to submit? Wind, dead and live loads. Yes. We have included gravity loads and also lateral loading. Among the gravity loads, we have included dead loads and live loads. In lateral loading, we have only included wind. Okay, now let's click on Edit Materials. In the Edit Materials, you have concrete columns. The first here, there is a C3545. Okay. Then next is the grade 500 type 2 and then rebars. Now, C3545, that is the grade of concrete. Now, the grade of concrete that we are going to adopt, you get it from the mixed design. You do a mixed design. Okay. So let's adopt a concrete grade of C2025. Click there and then choose C20, 25. Click on C20, 25, and then click on apply to all members of this class in the story. You mark that and then click OK. You find out that walls, beams, slabs, they have also adopted the same concrete grade. So what is C20, 25? Yes? Now, C20, this is cylinder strength. Have you studied about the different tests which are done on concrete, quality control tests? Okay, among the quality control tests performed in reinforced concrete is compressive strength test. So it is in the compressive strength test that you verify the grade of concrete to be used. So the grade of concrete we are adopting is C20, 25. C20 means that this is a cylinder strength. When they are testing that concrete in the compressive strength machine, you cast cylinder molds and also cylindrical molds and also concrete tubes on site. Okay, so when you are in the process of testing, if you're using a cylindrical mold, you aim for a value which is not less than 20. Okay, this is the cylinder strength. If you're using concrete tubes, you aim for a value which is not less than 25. This is what it means. This is cylinder strength, tube strength. So these molds have standard measurements. So it's a cube. All sides are 150 mm. That's the standard measurement of a concrete tube. Then standard dimensions of a cylindrical mold, the diameter, I think this is open, this is closed. The diameter here is 150. And then the height of that cylinder is 300. So that's the standard. Those are standard measurements. Now we go to grade of steel. When you click there, grade 500T, you notice that it is already in 500. So Eurocode has a clause which relates to the design, the grades of reinforcements, the range. It is in a range of 400 to 600. But what is on the market is usually the grade of 460 and 500. And in most literature, you find that those are the grades that are being used, 460 and 500. If you opt for a grade of 460, you notice that the display character is what? If you click on 460, grade 460, what's the display character? Is T. The grade of 500, what is the display character? H. That is the H we have been noticing in our steel. So however much we can design for 500, but still change this display character to T. Just click that drop down arrow there and choose T. Then we also apply all members in the story. You mark and then click OK. that okay? Then lastly, now we go to rebar diameters. Under rebar diameters, what you need to do first is to select all. You click on select and select all. So that you remain with a blank selection. So I'm in the concrete column rebar table. Are we in the concrete column rebar table? So for our columns, we say that our minimum steel bar size is going to be what? We chose, I think, 12, isn't it? So we went with the 12. So I can have it 12, and then I include 16, I include 20. Why am I opting for these ones? I cannot go for 25. Even if I choose 25 here in my interactive design, okay, when I'm trying to correct what has the members which have failed, I will not get this provision of 25. Why? Because I set it like my maximum was 20. It was not among the maximum bar size. So let's begin at the 25. We put 12, 16, and 20. Is anyone asking a question about that? So let's click OK. I'm skipping walls because even if we make selections, it's not going to create any impact. Let's go to concrete beams. Where you have concrete beams, rebar diameters. No, don't apply to rebars, don't apply to all. So concrete beams, rebar diameters, select and select. So you can choose from, remember, our floor beams, we said the minimum bar size is 12 and then 16. Let's choose the same preferences as for columns, 12, 16, and 20. Then click OK. We go to slabs, rebar diameters, select and select all. Yes. No, for rebar diameters, still don't apply to all. But then for grade of concrete and steel, applies to all. So slab rebar table, I'm using from 10 and 12 only. Then I'll click OK. Then we go to rib beams, where we have rib, select and select all. We can have 16 and 12. You may find that in ribs, even bars of 10 be passing. But based on our structure, we can override it. Okay, so let's just have 12 and 16. Then we shift to links. In the links, let's select and select all and choose only 8. We choose 8. Then the rest, steel columns, steel beams, truss members, these ones, leave them out. You got the foundation floor. You start with the concrete grade 2025, apply to all members. Then the grade 500, apply to all members. Rebar diameters, select and select all. There you go. I was thinking you already captured the concept. Okay. So foundation floor, have we changed the concrete grade? Have we changed the steel grade? Where there is grade 500, you click there and choose grade 500, apply to all members, and then click OK. Then under rebar diameters, select and select all. For the foundation, let's adopt a 12, adopt a 16, and a 20. Basically, you notice that we use the same similar bar types for all the structural elements. But at the stage of design, we shall try to optimize where it has given you 20s and find that maybe we can also have the 16s. We shall try to iterate. So let's click OK. Then links, use 500. Use 500 and apply to all members. And then the rebar diameters, you choose only 8. Okay. After you click OK, then let us be back to the building analysis window. Are we all there? So in the building analysis, you click on close. Okay. Now, we want to run the analysis. It is very important to note that before running the analysis, first decompose the loads of the beams, okay, from the slabs onto the beams. Before you run the analysis, you need to do load decomposition. Okay. So you should be at story 6, the topmost level. Actually, it is even better. You drag this window and activate the 3D window. When you're in the 3D window, make sure that you see where the grids are. They are in the last story. So when you're going to do load decomposition, we are decomposing from top to the bottom. Under loading, click on load decomposition by FE. Load decomposition by FE. Make it to be at story 6, the last level. You click on loading, then load decomposition by FE. Are we all there? Load decomposition by FE. Are we there? Then check this point here, should be story 6. You look confused. It was saving. Is it okay now? Okay, so you choose the last story. And then click here, FE beam load decomposition, all stories. Now, what we are doing right now is called finite element analysis. Okay. So in finite element analysis, we are interested in decomposing the loads from this slab, and then they are transferred onto the beams, the nearby perimeter beams. But then that load is going to be transferred through these points which are attached to the beam. Okay? So finite element analysis about discretization of the entire slab panel into small target element sizes. So after it has been partitioned into different sections, the program is going to like make an integration and find out, okay, it's going to compute the results for this part, results for this part, results for this part, and then all independently. And then those results are going to be transferred onto the nearby beams through these density points. These are called density points. Okay. And then these lines of divisions, they are called density lines. Now, the target element size that is recommended, it shouldn't be less than 900 mm, which is 3 feet. Okay. So when you are decomposing your loads from the slabs, make sure that the shell element size is not less than, sorry, is not more than 900. Okay. It should be 900 or below. But then the more elements that you're going to have, that means the analysis, the more it will take time to run the analysis. So if your computer is not performing very well and you're working on a heavy project, it's going to crash. But based on the system requirements which we provided, I'm assuming that all your computers have the minimum system requirements. Let's keep it at 800. But if you have a smaller target element size, that means the accuracy is more. Okay, so keep it at 800 and click OK. Then click on continue. You'll notice that in your 3D those grids will keep on shifting up until it goes to the lower levels. So I might have created my model when it is perfect, and I forget to do load decomposition from the slab. Your results will be wrong. Okay. So once it has finished, it will give you that warning. That warning is not an error, but it's just trying to tell you that I have finished and the loads have been calculated. Just click OK. And you'll have a green tick here. Do we all have a green tick? It is still processing. How do your grid stayed above? I said, once you take it to the last story, click on FE, beam load decomposition, all stories. Don't just click on calculate loads. If you just click on calculate loads, that means you are only calculating at that particular level which you have selected. Okay. Yeah, because now there seems to lack continuity. I've just seen something which I need to explain further. Now, when you try to do that load decomposition and it is failing due to the issues to do with the mesh, okay? So that means that it has discretized this part, but then when it came to this part, the density lines are not continuous, okay? They are like this. That is how it is seeing it. So they must be continuous density lines at these density points. So in that case, I think you may have to remodel. And what brings about that is the misplacement of the joints. Because as long as this joint is in the same position with this joint, definitely this point must be in line with this point. You get it? Yeah. For ribbed slabs, we already, okay, we provide FE strips. For it, we don't do meshing. This meshing applies only for solid slabs. where we shall have to do analytical strips, and then the analytical strips will take the results of this partition. Yes. Yes, we have the ribbed slabs, but then the loads that are being looked at here, they are loads of the solid slabs, not ribbed slabs. For ribbed slabs, they're already connected to the beams just by virtue of their span direction. It is okay. So we are at that step. You have the green tick, you click on close. This step is very important. As you close, you need to confirm that you are applying all beams to all beams in the model. If you click on story, that means you're applying those loads in the plinth beam level, which in the plinth beam level, you don't have slabs there. So you do in the model, so you have already got one report so far. The report that you have got is to do with axial load decomposition. Now let's click on analysis, then building analysis. Analysis, building analysis, then click on analysis again. So building model check, we are already okay. We started with checking our model to see if the joints are okay. So everything is okay. So you just go straight to building analysis, but we have this display analytical model. You can keep it there. You click on building analysis. How? You click on building model check and then click OK. Why you click on building model check is for you to see this learning as whereas regarding overlapping members, once you find them there, it will give you. So this is quite low. You will not proceed to post-processing, and it is in post-processing that we do design. You get it? So you need to make sure that all those errors are fixed in case they are there. But some of the errors, even me, I've never seen them. Because it is after you've done a mistake that you get a workout how you can correct it. It helps to identify that it points specifically which element has a problem. If it is overlapping members, it tells you beam this and this are overlapping. You look for that element. So let's click on building analysis. Click on building analysis. Now with ProtaStructure, you can save time. You can do design and analysis at the same time. So right now we are just at the analysis stage. If in case I want to command design, I can mark here that do column design, do beam design with the reselection of rebars according to the preferences I have set already. You get it? If you want, you can do it that way. So, but now, let's not do it that way. To save time, because it will take a lot of time to run the analysis and then it does the designs. So yet we need to do design in depth tomorrow. Now, let's unmark everything and then click on building analysis. Now you see this beam 1B60 at story 1 has a problem. The beams listed above may be cantilevers. If these beams are marked as cantilevers, this warning will not be issued in the future. So Proto is trying to tell you that there are some beams which it thinks they shouldn't be cantilevers, but they are marked as cantilevers. Do you want to proceed that way? Say design is, there are some things which are done intentionally. Okay, so that we intended for those beams to not be cantilevers. Let's just click on proceed. I'm sure your computers have already finished. You guys have powerful computers. Now, analysis summary report. Does it show that relative solid drifts satisfy limits? Then click OK. After you've clicked OK, it will open the analytical model. Let's click on close. Once you have closed, you already have the axial load comparison report. You click on axial load comparison report. This is among the reports that you have to attach. So click on axial load comparison report and it will be launched like that. So what is the axial load comparison report about? It will show you what you have applied, the magnitude of loads you have applied, both dead and live. Then load comparison. Now that axial load comparison report is about, it shows you what you have applied in the model in relation to what has been decomposed to the beams, all those loads from the slabs. Now, when you look at dead loads based on slab loads, these ones have been applied. Dead, the total is this 15,684. And then live, it is 19,602. I'm very sure I have different values from yours. Okay. Why? I have wall loads which I did change magnitude. Okay. So the magnitude of the dead load is going to be different. So what has been decomposed? Here I've applied 15, it has decomposed 15,559. So there's a difference of 100 something, which has not been decomposed. So likewise also for the live loads. So once you get that report, you click on to Office, then you save it to Word. And then click on where you want it to be saved. Let's say under this folder. I'll create another folder here. I'll call it report. I'll give it a name output. So I'll save it as actual load comparison. Once you save it, it will open Microsoft Word. And you can easily edit this report. You can remove this header. This is a header, double click there, delete that table. Now, this report has a header, which is a bit different from what you are seeing. So we are going to look at the reports manager, actually to make it simpler for you. That's the kind of report that I need you to create. Okay. So in the reports manager, that is where we configure all this. Company logo, training project, this is the project name, which we enter the other side. Okay, but you can edit all this information. So I'll close that report without saving. Also close this window. And then you confirm that building analysis is marked green. When you are in building analysis, when it is active, I'll close. That means that now I have the analysis output in terms of bending moment diagrams, shear force diagrams. I have the base reactions, okay? I have the shear stresses. Everything is there. Now, where do we get all that? Is from that analytical model window. Say when you're running a building analysis, there's that option which displays that display analytical model. Once it has finished run the analysis, it will open that window. There's even no need of creating, having this 3D now. Close it. Then I'll look at the analytical model. Analytical model, it basically means that it's a structure which has been represented in form of just lines, okay? But we can be able to put it in the different presentations that we want. For example, if we need to have all the structure elements display with their properties, you can click on solid model. Where we have solid model here, and it will give you a solid model in your project. This solid model is accompanied by a legend, which legend is showing some values which I also don't know as per now. Okay, so these values, they have different colors. According to this color, you can check the intensity of the stresses where it is on the structure. So what are these values? Let's head back to results. Those values we have been seeing are in relation to this component N. Okay, so N this is axial loading. We need diagrams for the axial loads. Click on diagrams. Okay. So when you click on diagrams, it will bring up your project like that, but literally, and nothing will be readable there. You can't read anything. Okay. So if in case you want to take off some values, you need to do some kind of sorting. You're going to look at maybe a particular grid, like for example, if I need to have values, let's say, what is this? This is grid A, okay? So grid A, I have a filter section here. This filter section has an auto hide button. There's an icon which is there called auto hide. Once you click on it, it will hide that information. And once you just point there to bring it back. So I need to lock it permanently there. So I'll click auto hide again. We have seen that icon. It is this icon here, auto hide. Have we used auto hide in AutoCAD? Also, this one works just the same way. And that is the icon we are trying to activate here. Okay, now I need to read off values at grid A. I'm just going to extract a bframe along grid A. So I'll look out for grid A. First of all, click on all axes to deselect all of them. Click on all axes, remove all of them, then I sample out grid A. So this is A. I'll mark A and I'll get this bframe. So I'm having these values. So when we are dealing with the axial loads, we are mostly interested in the bottommost load, because as you can see, it goes on accumulating from the top. So by the time the load reaches down, it is the highest, right? So if you intend to go through first principles, like to do foundation design, this is the value that you're going to design for this grid. This is 287 and this is 247. They are in negative. So the negative just means that it is in the direction due to gravity. So where we have them overlapping is you have a top reading for this column and also a bottom reading for the next column. That's why you can see them overlapping. But then what we look out for is this one, which is mostly at the bottom. Yes. First we talk about soil stress, you confuse them. But it is relating to something like that. Because this value is more than our soil stress. Okay, so the foundation which we should design should be able to carry this load. Okay, so based on whichever contact area of our foundation, we shall get suitable pad size. So for now, if I suppose soil stress, we shall talk about it when we reach foundation design. So this is the axial load diagram. And then if in case you need shear force diagram, we have V2 and V3. Okay, so V3 is a shear force diagram for columns. And then V2 is a shear force diagram for beams. Is this shear force diagram okay? Yeah? Is it okay? Because this is the time when you know that the software is giving you something right or something wrong. So considering a uniformly distributed load, we have a wall here. So is it okay? Yeah. For a uniformly distributed load, shear force diagram is 0 at the center, the maximum at the support. So this is okay. And then we have bending moment diagram, M22 and M33. So M22 is a bending moment diagram for columns. And then M33 is a bending moment diagram for beams. Okay. So is this bending moment diagram okay? Yes, I can see the hogging moments and also the negative moments here. Then, if in case you want to remove the labels, you can click on labels and you get a clear diagram, but having a diagram without labels will not have meaning. So you can click there to add on the labels. In case you want to increase the scale of the diagrams, you click on auto scale, remove it, and then adjust the scale from this area here. Okay. Deactivate auto scale and then use these arrows. So when I look at this, I can design for this area using this beam because it has the maximum bending moment. Have we come across this formula? Okay. Yes. This formula is for what? Fix end moments. Okay. So when you use those formulas, you compute and try to test these values using first principles. Now, all this diagram that we are seeing is due to a particular load case, and right now it is due to dead loads. You can click on this combination, click on whenever you click on a particular load here, that diagram is going to keep on changing. Meaning, if in case you are trying to go through first principles to design, for example, this beam, look for the load combination at ultimate limit state, which is going to be, it is this first combination, okay? This one. So when I'm designing, I'll click here and then read off these values. Now, put back all your axes and then deactivate diagrams and put displacement. Click on displacement. Okay. So when you click on displacement, are we able to see the extent of deflection? Yes. Are we able to see the extent of deflection for the structure, all these members? All this deflection, displacement, they are all in linear measurement. So it's under results, then displacements. Are we okay at that step? Where is the, so the all axis, it is here where you have the filter. You might have hidden it. Okay, just point there where there's a filter. You say axis, mark all axes. That okay? Yes. So we are okay at that step. Now, this is unidirectional displacement or bidirectional displacement. You can't tell because it is in only one direction. But by the fact that I have it here activated as bidirectional displacement, I can confirm. Okay. So you can turn on the animation here. You can click on animation, and then you'll be able to visualize the behavior of your structure. What they mean with bidirectional displacement is, you see, the moment this member deflects downwards, that means it has bypassed its neutral axis. And then if it goes down, it should be able to come back to the original position. But then it goes off its neutral axis up to the top. So it is bypassing its neutral axis twice. Okay. So the moment I make it, let me make it as unidirectional animation, you find that it will be only deflecting downwards. Have we been able to visualize that? One, there's only one thing moving. You know why it's like that? You can find that they are all moving, but then the scale at which they are moving, it is very minimal. You get it? Okay. So in case you want to see most of them deflecting, you may have to adjust the scale of displacement. You click on auto scale and then adjust the scale. If you increase it, they will deflect the more. You see that? Okay. Now, I'll get back to filter. I'll get back to filter. And where I am having members, where there's members, under members, we have frame loads. So this is how your loads are going to be distributed on your beams. You see, we are going through this just in case, because in the end, you need to prepare what we call a design philosophy. So in that design philosophy, you are going to take captions or snips of all these diagrams, the key diagrams, and put in your report. So that's the loading diagram. If in case you want it with labels, you click on that. But it's better not put labels because just mess it up. So tomorrow I want us to go into design and detailing. So I believe today's lesson has been the boring lesson, because there has been a few of click here, click here. There has been a lot of explanation, right? But it is the core. So let's do design tomorrow.